So today we are going to talk about one of the most significant shifts in modern iron making, moving from a block box operation to a transparent data driven hearth. For years the hearth was a mystery, but we are not using EMF or to gain proactive control over liquid levels. So we'll walk through the first principle, the math and the daily operation that makes this possible. But to understand why this is so important, we first have to look at the problems we have been trying to solve the decades. So, the black box problem. The core issue is that the hearth environment is a brutal, exceeding 1500 degrees centigrade with a corrosive melt and extreme pressure. So, making direct sensor insertion is just next to impossible. So look at the cross section on the screen. When we guess liquid level, we risk the black box failing us in three ways. We got floating deadman which disrupt gas flow, undetected refractory erosion that threaten the entire campaign, and unstable tapping that leads to dangerous splashing at the tap hole. So gazing is very expensive and it's dangerous also. Because of these risks, the industry has spent years evolving its sensor technology. So take a look at these. Uh, Comparison table. We have moved from sounding bars which were manual and low accuracy through radioactive tracers which carry high safety risk and radar which struggle with slag. Now look at the bottom row EMF. It is the new global standard because it's non-invasive, has low safety risk, and provides a high accuracy, real-time monitoring with an incredible plus minus 11 resolution. So, how exactly does this steel shell tell us what's happening inside? It starts with a galvanic battery effect. So this is the core concept. The blast furnace hearth is actually a giant chemical engine. As you can see, the reduction reaction near the interfaces of the hot metal and slag generate a natural voltage. We also capitalize on the conductivity gap. Molten iron is a superior conductor. It acts as a short circuit while slag is a million times more resistive. As the iron level rises, it shut out more, more of the resistive lining, and we measure that changes as a shifting voltage on the outer steel shell. So now let's look at the math that translate those chemical reaction into actual numbers. So how do we translate chemistry into voltage? We use the Nernst equation. Here E is a raw microvoltage we capture at the shell. It is strictly governed by the absolute temperature of the melt and the oxygen activity or PO2. So essentially every millivolt we measure is a direct mathematically predictable output of the oxygen activity and temperature interacting with your lining. With this math in hand, we can follow a simple 3 steps master class to get our final reading. So we follow a clear path, input, processing and output. First the sensor records a reading, let's say 250 millivolt at 1500 degrees centigrade. Second, we apply 4-point Kelvin probing method using Ohm's law to calculate the specific resistivity drop caused by iron accumulation. Finally, we translate that resistance into geometric height, converting that 250 millivolt signal into a specific prediction like 1200 mm above the hearth floor. To get this clean reading, we have to choose the right sensor architecture. So, choosing the right weapon. So, probe look at the two options on the screen. On the left is a legacy method, refractory embedded probes. While they offer a direct connection, they have a high failure rates from thermal expansion and create a severe risk of toxic gas leaks. This is why a shell welded probes are now the modern standard. They are 100% non-invasive, preserve your shell structure integrity, and only require advanced filtering to isolate the signal from background noise. So once we have selected our probes, we have to wire the entire system together. So as you can see, there's what is shown uh, very correctly what we have talked about. So the here is the journey from the shop floor to the control room. It will start with the circumferential sensor array on the shelf, travel through the shielded compensation wire to a junction box, and then across a wiring bridge. The signal then enters a 16-bit converter for noise filtering before finally appear on a SCADA dashboard as a real-time predictive data for the tapping team. Now let's look at a roadmap for actually deploying this system on your furnace. So roadmap phase 1 and 2, as preparation and installation happens in our four phases, starting with the uh, um, uh, during a spatial planning, we establish a ground reference and map our vertical levels. Notice the circumferential position relative to taffels. We place a sensor at 9 degrees 63, 171 and 297. That is on the fourth segment as the diagram shows. To ensure we see the whole hearth, not just one side. After the hardware is welded and shielded, we move into the validation phase. So in the next slide, we will show how to validate it. So as you can see, the challenge here is the industrial noise, AC oblique DC interfaces, interferences, and the thermal drift are it is shown. We solve this using algorithm filtering, like a extended Kalman filter to isolate the true liquid level uh, uh, transient. So during the first blow-in of the furnace, we monitor for the specific signal jump that makes the first slag formation. This establishes our permanent electrochemical baseline for the entire campaign. Now that we are up and running, what do the signal actually look like? So coming to our next slide, which clearly shows the signals and the tapping. This is our standard EMF wave. So during the feeling phase, the signal gradient rises as molten iron accumulate and shorts out the hearth. Once the taphole is opened, the signal drop. A sharp gradient indicate a rapid iron drainage, while a shallower gradient indicate the slower flow of the resistive slag. The trough of the wave confirms the hearth is truly empty before you plug the taphole. Beyond the standard cycle, this system acts as a diagnostic dashboard for anomalies also. So we can now spot invisible problems on the left, on the left. Uh, a specific single drop might indicate high FeO in the slag. In the middle, a stuttering signal tells you that coke pieces are causing a baffle blockage, requiring an immediate redrill or proper siphoning point adjustment after closing and again redrilling. On the right, a sudden spike indicates the slag peeling, where a protective layer has fallen off, as it is shown here. Mm, uh, causing a sudden shift in the conductivity. So this brings us a bonus capability, tracking the health of your furnace over a long period of time. Now, the decades of refractory health is also can be assessed with the help of such trends and profiles. Uh, so, as we can, as your carbon bricks erode over here, the physical distance between the conductive iron and the outer shell decreases, and a permanent gradual increase in your baseline EMF magnitude also keep on changing. So independence of daily tap tells you exactly how much lining is left. So these allow you to predict maintenance need uh, years in advance without any shutdown or running the operation. Or we can also monitor by throttling the wind or blanking the two-year what is the effect is coming to take care of those areas. So to make these actionable, we provide operators with a clear action matrix. So we can say that we use a sort of a traffic light system, uh, speed up or slow down, in order to take a precaution of campaign in mind. So we can see that green means healthy drainage, no intervention needed. Red means you have hit the upper threshold, prepare to open a tap full early to prevent a floating dead man. Or if you see the diverging signal across different sensor, it means the liquid is pooling asymmetrically and you should switch to an alternate taffle to balance the wear. So let's wrap up with a look at what this means for the future of your plant. So we have successfully transformed the blast furnace from a reactive opaque vessel into a transparent, mathematically predictable ecosystem. By mastering the electrochemistry and the signals, you are no longer just operating a furnace, you are managing a high-tech liquid control system. These results speak for themselves. Safer cast house, protected hearth, and peak iron making efficiency. The hearth is no longer a black box now.